Hi, this video will help you to understand fixed point implementation fixed point implementation code provided in your lab manual. First, we multiply a, which is 3.2 with 2 power 15 minus 2 to normalize it to 16-bit signed integer, and we do same thing with b, which is 2.7, and we multiply it with 15 into 2 power minus 2 to again convert it into signed integer. We are subtracting 2 we are every time subtracting 2 from 15 because integer word length for both a and b is 2, and we want to normalize, since we want to normalize a and b both to 16-bit signed integer, so that's why we are multiplying, finally multiplying it with 2 power 13. Moving ahead, this loop, in this loop we create xi array which has values from 2000 to 2099. These are again any random values, you can change it afterwards. So these values are anyways less than 2 power 12, so we can represent those values using these values using 12 bits of binary digit. And next loop, so moving towards next loop. So this loop again normalizes xi to 16-bit integer number, as we did with constants a and b, by multiplying each and every xi with 2 power 3. So as we say that xi integer word length for xi is 12, so we are multiplying it with 2 power 3, or we are live shifting it with 3 binary digits. Then moving ahead to addition and multiplication loop. So this function underscore LSMPY, which stands for left shift and multiply. This function does multiplication, and left shifts result by 1 digit to drop extra sign bit, which is generated when you multiply two sign digits. So we can finally we can write temp1 variable which is here in your code as a into 2 power 13 multiplied by x into 2 power 3 multiplied by 2. This 2 is there because we are shifting result to left by 1 digit. Moving ahead, so this there is one more function that we are using here, which is extract underscore h. So extract temp1. This function extracts upper 16 bits, so we can write temp2 is equal to temp1 multiplied by 2 power of minus 16. This minus 16 is equivalent to shift right 16 times. Again, putting values of temp1 from previous case, which is a into x into 2 power 17 and divided by 2 power 16. This comes to be equal to a into 2x, which happens to be equal to like maximum value, if we take maximum value of x, which is 2099, and yes, a is constant, which is 3.2, and multiply and take a result, then this turns out to be 15960, and which is again less than 2 power 14. So this means that we can represent this figure using 14 digits. So integer word length of temp2 is 14. Finally, y. Now we are interested in calculating y, which is lesser than 2 power 13 at any case. So we can. So I have calculated using calculator, and we are pretty much sure that it won't go above 2 power 13. So instead of directly moving to this step, first I will try to explain this stage, which is commented in your code, in code provided to you. So whenever I write f in front of any variable, take it as we are normalizing that with 16-bit signed integer. So y of f is equal to temp1, which is a into x into 2. Sorry, this is temp2 that we are writing here, and since now we have seen that it's less than 2 power 14, and we want to 2 power 14, and we want to normalize this to 16-bit signed integer, which has magnitude of magnitude is stored in last 15 bits, and 1 bit is reserved for its sign. So we need to shift it to again we need to shift it to shift it left by 1, and we are doing this because integer word length of a into x into 2 is 14. This clearly indicates we are not using its 15 bit. So to improve accuracy of computation by accommodating one more bit after decimal point, we are shifting it left by 1 by multiplying it by 2, or simply writing it like this, as we have done here, and then plus term b into 2 power 13, which we have done initially. So this entire thing is bf, and multiplied by 2 power something. So this sum, this value is there for alignment of decimal point. Now we if we go ahead now, as we know, this y is 13 bit, its integer word length is at max 13 bit, so we need to denormalize y of f. So for denormalization, we write y is equal to y of f, right shift by 2. Since integer word length of y of f, it is normalized, so it will be 15, so we are again right shifting it by 2, so to make its integer word length to 13, to denormalize and get accurate results. So if we replace y of f with above expression, a of a multiplied by x multiplied by 2 multiplied by 2 plus b multiplied by 2 power 13, it's 13, multiplied by 2 power something that we don't know. We will figure it out shortly how to calculate this value, and again multiplied by 2 power minus 2, since we are shifting it right by 2. So this is what we get. So in finally we want y is equal to a multiplied by x plus of b. So here you can say this 2 and this 2 will get cancelled with 2 power raised to minus 2, and if you want to cancel out this term, entire term, 2 raised to 13 multiplied by 2 raised to something multiplied by 2 raised to minus 2, here value should be minus 11. So 2 power 13 into 2 power minus 11 into 2 power minus 2. So which is the reason why we are shifting df value to right by 11 digit, and this is how we implement floating point arithmetic in fixed point processor, which seems to be a little bit tough, but which is more efficient as you see when you do profiling for normal floating point implementation. Thank you.